So I'm just starting. Thank you for having me. Second time after I missed the first one. I'm going to present a paper that we published beginning this year about the Atlantic overturning circulation and how we use air sea heat fluxes to infer changes since the 1960s. And it's a study that made partly in Bern and partly mostly in Woods Hole during a scholarship together with Nick Foucault and Linus Vogt. So for all of you who are not oceanographers, so just a brief overview or very simplified overview of the ocean overturning circulation globally. And we can see here that in the North Atlantic, we have the meridional overturning circulation with warm water moving northward. At the surface that cools and gets denser and then sinks below the surface and goes back south. In practice, it looks much more complicated, the circulation, and I'm not sure if we understand every detail of it so far. So it's a much more complex system of different intertwined currents, as you can see here. And yeah. It's a complex system, but it also is a very important system for the climate. It warms the countries around the North Atlantic quite a bit, and especially Europe. And if the system should break down or the AMOC should collapse, we would expect to see temperature changes that look roughly like this. So these are simulated temperature changes after doubling of CO2 and an AMOC collapse. So we see the global warming signal almost everywhere. We would see a drastic temperature decline in the North Atlantic, over Greenland and Scandinavian countries, the UK, and also with associated changes in storms, precipitation, and other climate indicators. So that shows how important this current and this circulation really is for us, and that's why it needs to be monitored. And this is happening at different areas. So here's one of these areas, probably the most well-known of them, the rapid area at 26.5 degrees north. And you can see a bit how, with moorings, how this is set up. And then on the right, you have the resulting overturning circulation measurements, the different component. And in red is the sums of the meridional overturning circulation. The problem is, these observations only started in 2004, so we don't have any measurements before 2004, at least at this area, and it makes it harder to understand how the AMOC has behaved before. And to understand this, a lot of people use proxies to test or to evaluate how it has changed before. And probably the most well-known proxy of them is the AMOC index that was developed by Ramsdorff et al. With the cold blob. So the idea is that if less warm water is transported northward, the temperatures in this region will cool. And then the AMOC index that is related to the AMOC strength would be the temperatures in the subpolar gyre, here marked as the cold blob, minus the global SSTs, so the difference in this region compared to the rest. And this was done with the CMIP models to test this relationship, how well the AMOC index really is, or how it scales with the AMOC anomaly. And you can see CMIP models that give a relatively good correlation. If you exclude models that don't simulate the historical AMOC, or are not close, don't simulate a historical AMOC that's close to the observed one, then you are left with the colored dots and a correlation of 0.94. And from this, if you use that linear trend here and the relationship, you can deduce then from the SST anomaly, the AMOC anomaly. And this is the blue line here, which indicates that the AMOC has decreased in the 1990s, recovered a bit, and is now decreasing again, and has a long-term centennial negative trend. So what we did is, in our study, we repeated the same analysis with the CMIP models. And this looks like this. So first, what you can see here is that the R squared, or the correlation, is much weaker than for CMIP models. That's the R squared is 0.5. And before it was around so it was an R of 0.95, so an R squared of around 0.8 something. So the relationship is much weaker in CMIP6 models, but also compared to the linear fit from the CMIP5 models, which you can see here, that the relationship is not only weaker, but it's different. So instead of 1.6 square drops, 3.8 square drops per Kelvin change in the AMOC, we now get a 1.6 from the CMIP6 models. And if you then try to deduce the change in the AMOC by using the change in SSTs, you can see here that we get an AMOC change from CMIP6 models of minus 0.2 plus minus 0.7 square roots per century, so not significant. And we are not the first ones who realized that the relationship is not as good as it seemed to be at the beginning. So there's another study by Olsen that they use 13 CMIP5 models. They find an R squared of 0.5, similar to what we find. And then there's a more exhaustive study by Minari et al. You can see this here, where they used 39 CMIP5 models and 25 CMIP6 models, also coming up with an R squared of 0.49.
U sociálních služeb nebo u pomoci dobrovolným hasičům nebo u sportu. Tak musí...
There's noise in the background. Is that just me?
Musí příští vláda, já myslím, že bude vláda Petra Fialy, pokračovat v dalších důležitých...
Thank you. And so this our study showing that this might not work as well as it seemed to be is in a range of different already existing studies. Another thing that here it's always looking at the trend, and the trend is maybe not the best metric. So if you look at this, for example, you have on the left the CNRM model where you get a strong negative anomaly in the 1900s, and then a positive anomaly towards the 2000s, and then in total that makes a positive trend, although you would not really infer a trend from this just by looking at it by eye, just a long-term variability. Or similarly, the MRI model here, you would also get a positive trend from this time series, but you wouldn't say that the AMOC has really increased over time, and there was just a positive anomaly at some point. And just to see how extreme this gets, so if you use this model, it's the one here at the top with the strongest increase in the AMOC and the strongest SST changes. Just it looks as if the AMOC has increased, but it didn't really do that. So what we did then instead is we looked at annual and decadal and centennial averages to see if we just look at one time series, if we can, at one point in time, if we can relate the AMOC to the SST index. And we got this. So it's basically just a big cloud. The R squared is really low for annual averages. We then tried decadal averages, trying to filter out noise. It gets a bit better. But still, you can't really, it's hard to find or to relate both variables statistically. And then on centennial averages, it gets even worse again. So this means that we need to look at something else. We need another proxy, really. And the proxy that we are suggesting is to use the RC heat flux, because we just looked at the heat budget. Looking at the ocean heat content change is basically the sum of the meridional heat transport from the south, what goes out to the north, and then the net RC heat flux. And if you look at the components, you can see them here for 18 models from CMIP6. I zoomed out one to show this. So the heat content change in blue is on average, in most models, is relatively small. And we have the northward heat flux anomaly, so from the AMOC and green, and it's mainly compensated by the RC heat flux anomaly. So these two quantities are really the strongest one in the budget. And the idea that we use then is that if you look here at the North Atlantic as a box, you have the meridional heat transport from the south, and if that increases, you just lose more heat to the atmosphere, and if that decreases, there's less outflux to the atmosphere. We then tested how well that works across the CMIP6 models. What we find here, so this is the AMOC correlate shown against the meridional heat transport, which is not a surprise that they correlate very well, because most of the change in heat transport doesn't come from changes in temperature in the water, but from the water volume. And then we correlate the meridional heat transport, or we plot it against the North Atlantic RC heat flux anomaly. And that gives us also a very strong relationship, as we expected from the different components in the time series that I showed you before. And if we put that together and plot the AMOC against the North Atlantic air sea heat flux anomaly, we get this plot, and we see that the AMOC and the North Atlantic air sea heat flux anomalies in the models are very well correlated on decadal and centennial timescales, and on annual timescales we have more noise in the system, probably induced by the atmosphere or ocean heat content changes on small timescales. So if we use this relationship, we can on decadal timescales or decadal averages, we can reconstruct the AMOC. And we did this in models to test how well it works. So we took out one model to out from the calibration to get the relationship. And then we used the model's air sea heat flux to reconstruct the AMOC in the model. And what we find here is we have here for the MPI ESM, we have the directly simulated AMOC. And this is the reconstructed AMOC based on the air sea heat fluxes in the model and the relationship that we found. And then if you plot them one on top of each other, you see that the reconstruction works very well. It's with the uncertainty bars. Here is it for all 24 models that we used. And you can see that the reconstruction works well in most cases, but on almost all. And then we have a few exceptions coming towards the end of the time series, so around up to 2014 here. And we see that the reconstructed AMOC in some models is lower when it declines than the actual simulated AMOC, so that the reconstruction overestimates the decline. And the reason for this is that all these models here are models that warm very fast, that have a high climate sensitivity. And if we go back to this box plot, if we look at if we have global warming that is very strong, we get an additional air sea heat flux that manifests in ocean heat content change, but not in changes of the meridian heat transport from the south or from the AMOC. So what basically happens if we get an additional air sea heat flux anomaly without the AMOC anomaly change because of the global warming signal. And if we then use this North Atlantic air sea heat flux anomaly to deduce the AMOC, we would deduce this value for the AMOC, so we overestimate the decline, which basically means that if we see a decline in the reconstructed AMOC, it might be really the AMOC that is declining, or it might be additional warming from the atmosphere. However, if we don't see a decline in the AMOC based on the air sea heat fluxes, we can be sure that the AMOC has not declined, because the only way that it would move it would be if we had a global cooling, and we definitely don't have that. So what we did then is we used air sea heat flux estimates from reanalysis data to reconstruct the AMOC in the real world, not just in models. So we used this relationship and the estimate of the air sea heat fluxes, and we used ERA 5 and JRA, and we come up with this time series at 26.5 degrees north. And so the error bars are plus minus 1 standard deviation based on the linear fit. There's no uncertainties from the estimates of the air sea heat flux because we just don't have them. So this is just, the uncertainties are just from the relationship. And the two time series agree within plus minus 2 sigma range. And there's only this small spot here where they don't agree within plus minus 1 sigma, but this given the number of years that we have here, it is expectable that they don't always agree. And it gives a first idea of the whole uncertainty also associated to the air sea heat flux estimates. And we just get a slight positive trend in both time series, but not a significant positive trend. And this is basically our main result. And as we use the heat budget and compared to just looking at the subpolar gyre, we have the advantage that we can do or reconstruct the AMOC at different latitudes. So if we do the heat budget not at 26.5 north, if we just look at air sea heat fluxes north of 30 degrees, we can reconstruct the AMOC at 30 degrees north. We can do that at 35, and at 40 and 45. And here are the reconstructions at the different latitudes. What you can see is that they don't all, that the AMOC is really different. I mean, we knew that, but it's just a nice way to see it again, that the evolvement of the AMOC is different at different latitudes. So it's not just a single conveyor belt. It's a much more complex system.
You've got a couple of minutes now, Jens.
Thank you. I'm almost wrapping up. So we used RC heat fluxes, but as I said, they have their own uncertainty. And if you look, for example, at global RC heat fluxes compared to what goes into the ocean and these estimates, so we have here error 5. This would be the ocean heat uptake or the ocean heat content change by 2014-16, and this is the observed ocean heat content change. So globally, these estimates either take up too much too high RC heat flux or too low. We can see that here how that's distributed over the regions. So, for example, ERA 5 has too much heat uptake in the Southern Ocean. And in general, what we see in the North Atlantic, the uncertainty or the biases or the necessary adjustments are fairly small. And they're especially small in core V2, which we hadn't used in our study because it doesn't cover the entire period. But I just want to show you that time series for when we have the data for this RC heat flux estimate that has the lowest biases. And if we add that to the time series, it looks like this. So it looks fairly similar to the data that we have, in supporting the idea that we can use these data sets and also at different latitudes. It agrees well with the other estimates. So to wrap up, we believe that RC heat fluxes are a better proxy to reconstruct the AMOC on centennial and decadal time scales, and we can use it at various latitudes. Based on the reanalysis RC heat fluxes, the AMOC appears to be more stable and potentially more robust to external forcing than previously thought. And as the reconstruction of the AMOC also shows less change than the change in the CMIP models. First, they don't show the increase, and then it doesn't show the strong decrease in some models. So it might be that the ESMs are too sensitive, and the AMOC might decrease, or the AMOC might be too strong. And for the future, RC heat fluxes may provide a complementary and relatively cheap way to detect AMOC changes. Thank you very much for your time.
Thanks, Jens. That was really good. We've only got a couple of minutes left, so there's a question in the chat that I'll just ask. Frederick Bono asks, and I was thinking this as well, what makes the difference between what's this difference between AMOC from CMIP 5 and CMIP 6? Why is there such a difference?
I think there's not really a difference because we repeated our analysis for CMIP 5 models for the RC heat fluxes, and we get the same results. So if you plot RC heat flux anomalies in the North Atlantic against AMOC anomalies, you get the same relationship from CMIP 5 than you get in CMIP 6. The difference that is what we get here from CMIP 5 to CMIP 6, I think, is so for the SSTs, there's the difference. But if you look again at the Minari plot where they used more models, the difference disappears. They look fairly similar, the two model groups. Yeah. There's some models that stand out here because they have they are too sensitive to aerosols. But if the large number of models show the same relationship, so I think it's just an unlucky selection of too few models used in the previous studies. Then that gave a bias. It might be just these models that were a bit different. But if you take all models together, I think it looks like to me that the relationship is also for SSTs the same as in CMIP 5 than in CMIP 6.
Okay, thanks a lot, Jens. There's a Helen Hewitt's asked a question in the chat. If you could just share your reference for your paper, if possible, if you could put that in the chat.
Yeah, I can share that in the chat, yeah.
And we'll move on to the next speaker if you could stop sharing your screen. Thank you.
Yeah, of course. Thank you.